Okay, good morning. So let us start the new lesson, but unfortunately I think the projector is not working either today. So it would be a good idea if you have the notes in front of you. It's not that important, I can write what we need on the board, but if you have it in front of you, that might be better. Okay, so today, the first thing we want to talk about today is the topic of related rates. So what do we mean by that? So usually, for example, you can have a quantity y which depends on another quantity x. For example, when you write y is a function of x, it means that y depends on the value of x. Y is a function of x. And then, of course, you can talk about the derivative. But usually, because in this topic we have more than one variable involved, it would be better if I write the Leibniz notation for that so that we know what does this prime mean. So here y prime, if I mean, I can write it as dy dx. Okay, so instead of using this old notation in this topic, it would be better if I use Leibniz notation. So when I write dy dx, it means that I want to know how sensitive y is to any change of x. In other words, the dy dx is the rate at which y changes when x changes. Okay, but now let us assume that this x itself is function of another variable. Usually in this topic we call it t, because usually this is problems from physics and things like that, so t is the time variable. Okay, so then of course here I can also talk about this dx dt. Yes, what does it mean? It means that, forget about this part, x itself is a function of time or function of t. I can also differentiate x with respect to t. I want to see how sensitive x is to any change in t. Okay, but you agree with me that when y depends on x, x itself depends on t. In an indirect way, y also depends on t. Yes. So in principle, this is also meaningful. So this time it means that how much y changes if t changes. Of course, if you want to think the change in t causes a change in x and the change in x causes a change in y. So in principle, we can also talk about this. So these are three quantities, three derivatives that we can talk about. But hopefully you know the rule, yes? What the rule is. For example, if y is a function of x, so let me write y is f of x. And x is probably another function of time, and so let me write it as g of t. Okay? So then if I want to connect y directly to t, what should I do? In these two equations, I replace x with g of t. So then y becomes f of g of t. So y is f after g. Yes? So this means that this is f of g t. So if I want to calculate dy dt, if I want to calculate the derivative of y with respect to the last variable, in principle I should use the chain rule. So this is not a new topic, this is an application of the chain rule. So how should I write that? So if I want to answer this question, do you remember? It becomes f prime calculated at g of t multiplied by g prime of t. Yes? That's the chain rule. But usually in this topic we write it like this. So we say that dy dt, yeah, if you want to be a little bit sloppy. So what can I write for g prime of t? So g is the function of x, so people usually write it as dx dt instead of g prime of t, which is the derivative of x with respect to the variable. And this is the derivative of f, which is dy with respect to x. So this is actually a simplified version of the chain rule. So if I want to calculate the derivative of this variable with respect to the last variable, I can take the derivative of y with respect to the intermediate variable, but I have to remember to multiply by the derivative of the intermediate variable with respect to the last variable. It's just a simple way of remembering the chain rule, which is simple for this text, for this context. More or less, is that understandable? So I'm not telling something new. I'm just using the chain rule to solve some problems. So I have written some problems here for you. So let us go through them. So this here, if you see it, related rates. This is more or less a copy paste of your course books for completeness. So you don't, some advice how to solve these coming problems, but I think this is much simpler. You don't really need to really remember these things. So example 1, let's just read it. Air is being pumped into a spherical balloon at a constant rate of 4 pi cubic centimeter per minute. What is the rate at which the radius of the balloon is increasing at the instant the volume reaches to 36 pi cubic centimeter? Yes? Is the problem clear? So I have a spherical balloon. I am pumping air into the balloon, so the volume of the balloon increases. And I know that how fast the volume is increasing. It is mentioned in the problem that the volume increases in a constant rate of 4 pi cubic centimeters per minute. 4 pi cubic centimeters per minute. Okay, when you read this, what does it mean? So if I show that V is the volume, and for example, I say R is the radius. Okay, so by reading the first sentence, what can you write? It means the rate at which this quantity volume is changing over time is a constant value, which is given to be 4 pi cubic centimeters per minute. So when you read this, you understand that this problem is given to you. This is given to you. But by the way, at any instant of time, so if you want to be very cautious, you have to put this dependence t here, but on the right hand side, according to the problem, that's constant. So it doesn't matter at which time I am looking at this, the rate at which the volume is increasing is always that. Okay? So this is what I write by reading the first sentence. What is the rate at which the radius of the balloon is increasing? So what is wanted? The radius, what is the rate at which the radius is increasing? So we want to know what is the rate at which the radius is changing. So this is my question mark. When at some point, so in principle you have to write t here, t naught. At which point? At the point when the volume is 36 pi cubic centimeters. It means that V at that time for which the volume reaches to 36 pi cubic centimeters. Yes, is that clear? So that's what we understand. But usually in these problems, we don't write these T naught. In principle, this means that, but let me make it simple and just write this. Okay, so is that clear? So I am pumping air into the balloon. Of course, the volume is increasing. So, and then it means that volume, the radius is also increasing. We want to understand how they are connected. Okay, so here you need to know some formulas. There is a formula that connects the volume of a sphere to its radius. Yes? So what is the formula? I don't know if this problem is given in the exam. Are you supposed to know, I think, the formula? Yes? This is the formula that connects volume to the radius. So here in this problem, volume depends on the radius, but because of the structure of the problem, radius is not constant, radius is also changing over time. And by the way, you can think it the other way around. You can say that the volume depends on, the radius depends on volume, and volume depends on t. This is more natural for this problem. But I will to use this one because this will be algebraically a little bit more complicated, but I want you to know there is no difference between them. Okay, so I have this quantity, and I want to know this. So whenever this happens, I differentiate both sides with respect to time. Okay, so this means that I can differentiate v with respect to r, but I have to multiply with derivative of r with respect to t. Okay. So dv dr is very clear. So it means that differentiate this function if r is your variable. It means that this is like an x. So if I want to differentiate it, what will be the derivative? Derivative of this one if r is the only variable in the problem. So you treat it as if r is x. So 3 goes down, so it becomes 4 pi, and then you will have r squared. So this is this quantity that I'm writing, but I have to multiply it by dr dt. So I shouldn't forget about that. So let me write one more. dv dt is equal. Okay, so what is wanted? This is given to me at any instant of time, so instead of that, I can write 4 pi with that appropriate unit. dr dt is my question mark, so I would write 4 pi. dr dt is my question mark that I am looking for. But I also need to know r, because you see, this is my question mark. If I want to know the question mark, everything else should be known to me. So I have to put something for r as well. What can I do about it? I am interested in this calculation at a specific moment in time. What time? The time that volume reaches to this value. Okay? So from here, you can see that the volume is 4 pi, 4 over 3 pi r cubed is equal to 36 pi. Then this will allow me to calculate my unknown r. So pi's are cancelled, so r cubed becomes 27, and then of course r becomes 3, and everything is, so the length is measured in centimeters, so r is 3 centimeters, and that is that r that I have to move and put it here. Yes? And then of course this 4 pi and that 4 pi are cancelled, and dr dt is equal to 1 over 9, but you have to write the units. Every length in this problem is measured in centimeters and time is measured in minutes. So it becomes centimeters per minute. So that is what we're supposed to answer for this question. So this is the way that you usually should do the problem, but I would recommend you to write this formula and then write like this, dv dt, immediately. So you remember, when you write dv dt, but you need to know r is not like x. R is a function of another variable. So you always use the chain rule. So you don't really need to do any of these mess. So if you want to calculate dv dt, I just differentiated, do you remember, u to the power of 3 prime, because of the chain rule is 3u squared, but multiplied by u prime. So here, v is a function of time, so v relates itself to r, but r is not an atomic, how can I say, is not an atomic variable. Inside r, there is a t variable, so it depends on t. So when I want to differentiate with respect to the inner variable t, I have to use the chain rule. So it means that I would write it as 3r cubed, but I have to multiply by the derivative of r, but because the t is not written in the problem explicitly, if you just simply write r prime, people get confused what r prime means. So what we do, we actually write it dr dt. So this is the way I really do it myself. So this is a little bit faster. So you really don't need to write those steps. Okay, and then everything else will actually be the same. So from now on, I will use this faster way, but you'll understand that this is nothing new, it's just a chain. Okay? So let us go to the next problem. Any questions here? So might be in the next question you will understand it a little bit better. So let us read it. An aircraft is flying horizontally at a speed of 600 kilometers per hour. How fast is the distance between the aircraft and a radio beacon increasing and a radio beacon increasing 1 minute after the aircraft passes 5 kilometers directly above the beacon. Yes. So how can you assess the problem? So an aircraft is flying horizontally. So let us say that this is the ground level. An aircraft, I don't know, so for example, this is your aircraft, is actually moving, for example, to the right at a speed of 600 kilometers per hour. So the velocity, the speed of this aircraft is 600 kilometers per hour. Okay, what is the rate at which now how fast is the distance between the aircraft and a radio beacon increasing 1 minute after the aircraft passes 5 kilometers directly above the beacon? For example, this is your beacon here. When this distance, when it passes exactly above that at a distance of 5 kilometers, after 1 minute, this airplane probably will be here. And then I want to see how fast the distance between the airplane and the beacon is changing after 1 minute. Okay? So I am interested to know if I call this distance, I don't know, S. So I want to know that how fast this distance is changing 1 minute after the instant that this airplane passed exactly above the beacon, which is 5 kilometers above. So I don't know, is the problem clear? So this, we want to see how fast this is changing. By the way, when we say how fast, what does it mean? The derivative with respect to which variable, of course, time. So always the word how fast means calculate the derivative. So in principle, we want to somehow know ds dt, somehow. Okay? Okay, so every time you want to solve these kinds of problems, you should have a function so that you can differentiate. So you need to write this s as a function so that you can differentiate it. So what function is that? So you have to understand the function yourself. So here it was very simple. The volume relates itself to the radius using this formula. But here you have to be sometimes creative to find your own function. So what can I write here? So this distance is known to you or not? No, because it is, yes, it is known to us because I know the speed and I know I am interested at which time. Yes, we don't know that because this is changing. So let me call it, what do you call it? For example, it is good to call it x. So you see that x is a function of time. It changes over time. This is fixed, this distance. And s also consequently changes over time. Okay, but do I know about the rate at which x changes? Yes, because that is exactly the velocity. So this means that dx dt is given to be constant 600 kilometers per hour. But I want to know ds dt. So I have to be able to connect somehow s to x. If I have that connection, then I can start differentiation. But the geometry is extremely simple. Can you see how can I connect s to x? Pythagoras theorem. Yeah, so because, assuming that this is 90 degrees, so I can write that the hypotenuse squared is equal to 5 squared plus x squared. So if I want to write it, so this becomes s squared is equal to 25. And then I have, by the way, you have to be very careful about the units. So this is kilometers and this is kilometers per hour, so it is consistent. Okay, so what do you suggest now? One idea is, okay, I want to find s because I want to differentiate s. But we already learned about implicit differentiation. So it would be better if you do implicit differentiation. Of course, in this case, it is very simple. You can find s as a function of x and then differentiate. But there is no need to do that. Start differentiation on both sides immediately. But what is the variable of interest now is time. So I would differentiate the left-hand side with respect to t. I should also do the same thing. I should also differentiate the left side and the right side with respect to the same variable t. Okay? But now be careful. S itself is a function of time. So it is something like this. So you shouldn't write 2s. You should write 2s multiplied by the derivative of s with respect to time. So it becomes ds dt. Yes? And on the right hand side I have two terms to differentiate. The derivative of this constant is 0, so I don't need to write it. But the derivative of x squared is not just simply 2x, because x is a function of time and I'm differentiating with respect to time. So this is 2x, but, can you tell me? Dx dt. So that is a simple way of differentiation. Okay, so these two are cancelled. So don't get confused. This quantity is the question mark. This quantity is given. Is 600. Okay? What I need to know, if I want to know this question mark, I need to know s, I need to know x. Because if I know s and x, I already know that, I divide, and then I find ds dt. Okay? But how can I calculate x? X is very simple. X, at which time I am interested to do this calculation? At 1 minute after this passes. So 1 minute after I can calculate x, very simply. So 1 minute after, 1 minute after, so x becomes what? 600 kilometers per hour, but 1 minute is 1/60 hours, because the unit should be consistent. Yes? So the answer will be what? The answer will be 10 kilometers. Okay, what about s then? Because I also need s. Very simple, I just write s squared is equal to 25 plus this number squared, yes? So it becomes 125. So at that moment, s is the square root of this one, which I can write it as 5 square root of 5 kilometers. So be careful, so include the units. So here x is also 10 kilometers per hour, 10 kilometers. Okay, so then I can write this equation, for example, number 1, and number 2, and number 3, so I can use them. So number 1, number 2, and number 3, I can conclude that instead of s, I put 5 square root of 5. ds dt is exactly what I want to calculate, but the right hand side x is 10, and then dx dt is 600. So what happens then? ds dt, so this becomes 1200, because 5 and 10 are simplified, divided by square root of 5, that's it. But you have to include the units. What are the units in this case? S is a length. In this problem, length is being measured by kilometers, so this becomes kilometer. And then what is time here? Hours, yes? Understandable? Mm-hmm.
Yeah.
Okay. Let us solve two more problems. So might be we can solve some of them, because sometimes they might be a little bit hard. So you have to find the connection. So for example, the next problem is very simple. How fast, number 3, how fast is the area of a rectangle changing if one side is 10 centimeters long and is increasing at a rate of 2 centimeters per second, and the other side is 8 centimeters long and is decreasing at a rate of 3 centimeters per second. Okay? Okay. So how should we solve number 3? So we have a rectangle. So I don't know, if you want we can call the height y, the length x, for example. So what we know about this rectangle? How fast is the area? So I want to write the area. Let us call the area A. Okay. I want to know, so A, the area. So I want to know how fast the area is changing. So how fast, whenever you say how fast, it means you are interested in calculating the derivative of that quantity with respect to time. So this is wanted. But what is it telling you? It is telling you that one side is 10 centimeters and it increases at a rate of 2 centimeters. So x here, the length is 10 centimeters and it is increasing. So it means the rate at which this length is changing over time is also given to be 2 centimeters per second. So I'm just reading the question. I'm just drawing some picture for myself to understand it better, and I'm just writing down all the quantities in mathematical symbols. Okay. And then the other one is telling you that the other side is 8 centimeters. So the other side is 8 centimeters. And it is decreasing at the rate of 3 centimeters per second. So what should I write now? Minus, because it is decreasing. So you have to put it like this. So what I have done, I just read the problem, draw some pictures for myself, and write the quantities in mathematical form. So what is your suggestion now? My question mark is that how fast the area is changing. So how should I do that? I have to connect all these variables into a form of an equation. For example, in this case, the formula was the volume of the sphere. In that case, I use Pythagoras theorem to connect S and X. So here, I use which formula to connect all these variables into one formula?
A equals to
A is just x, y. It's very simple. So what I write is that A is x times y. So I'm not even, it's extremely simple. But now, I differentiate both sides with respect to time. But be careful, in this differentiation, x is a function of time, y is also a function of time, consequently a is also a function of time. So what I would write, I would say that dA dt is equal to d dt of this quantity. But this is a product, so I have to use the product rule. It becomes the derivative of the first one with respect to time multiplied by the second one, plus the other way around, the first one multiplied by the derivative of the second one with respect to time. Yes? And the problem is solved, because that's my question mark. dx dt is 2 centimeters per second multiplied by y, y is 8. And then x is 10, and dy dt is minus 3. So if you calculate that, this is 16 minus 30. It's minus 14, but you have to write the units. So what units do you think I will write here?
centimeter squared.
Because this is the area. So area is length squared, but in this problem, length is being measured in centimeters, so A becomes centimeters squared per second. So in principle, the area is also decreasing, it's not increasing, yes? Okay, let us do one more problem. So let us do two of them together. Okay, so example number 4. So example number 4, a lighthouse L is located on a small island 2 kilometers from the nearest point A on a long straight shoreline. If the lighthouse lamp rotates at 3 revolutions per minute, how fast is the illuminated spot P on the shoreline moving along the shoreline when it is 4 kilometers from A? Yes? Usually it's good to read the problem 2 times, okay? So you can read it yourself now. and try to draw some kind of picture for yourself, yes? So I don't know, for example, let us say that this is the shoreline, and then I have a light bulb here. What is given to me, it rotates, this lighthouse bulb is rotating 3 revolutions per minute. So usually in physics, when something rotates around itself, it is called angular velocity, and it is denoted by omega, but it really doesn't matter which symbol you use for it. So it is 3 revolutions, yes, per minute. Per minute, is it minute? It is minute, yes, per minute. Okay, but revolution is not a good quantity to work with. Let us work with radians. So every revolution, every complete revolution is 2 pi radians. So what can I write? So it becomes 6 pi radians per minute. So this is the frequency of this light bulb rotating around itself. And of course, it will illuminate a point on the shoreline. Yes. For example, if the light bulb, I don't know how should I draw it, but if the light bulb is like this here, it will probably illuminate this point P here, according to the problem. And it is also mentioned, it is 2 kilometers away from the seashore. This is what I understand. But hopefully you see what is going to happen. When I start rotating this, this point will also move on the shoreline. Yes? So we know how fast we are moving this, we are rotating this. We want to know how fast this point P is moving. Is the question clear? So I start rotating. So whenever it is in this direction, this point is illuminated. But when I rotate it, there will be another point illuminated. I know how fast this is rotating. It is rotating 3 revolutions per minute. I want to see that at some particular instant of time, what is the speed of this illuminating point on the shoreline? Yes, is the question clear at least? Okay. So let me see if I have written all the data on the problem. So the nearest point A, so this point is called A in the problem on the straight line. If the height rotates, how fast is P is correct? When it is 4 kilometers from A. So I am interested at that moment which this distance is 4 kilometers. Because this might be closer or might be farther away. I am not interested at the speed of B at any instant of time. I am interested when this distance becomes 4 kilometers. Okay? So of course this is not, this is a horizontal axis. Might be if I take this and I call this X, it's a better idea. Yes? So X is this one. But I know that in principle X is a function of time. So what are the quantities involved here? My information given to me is that how fast this is rotating, and I want to know how fast X is changing. Okay, so my question mark is definitely dx dt. Okay, but how can I use this piece of information into the problem? What is the meaning of the rate, the angular velocity? So you see it is the quantity radian. Radian is the unit of an angle divided by time. So it means that I should somehow write to find an angle in this problem whose derivative gives me omega. What is that angle? So this angle. Yes? The rate at which this angle is changing is exactly this angular velocity. Is that understandable? Yes? Because when I know that this is rotating at this constant rate, it means the rate at which this angle is changing over time is that constant value.
Is it sine?
No, I'm just talking about theta. So so omega is the rate at which this angle is changing. That's what I'm telling you. But then, of course, in order to solve it, either we use sine or cosine or something, okay? But I just want you to understand, have you seen it in physics? So if you have omega, omega is the rate at which this angle is changing over time. Okay, and it is given to be a fixed number. Okay, so this means that the quantities involved in this problem, on the one hand is theta, this angle, on the other hand is x. I want to have a connection between theta and x. And of course, you either use sine or cosine or tangent, but which one is more appropriate to this problem? Because sine and cosine are related to the hypotenuse, and I don't have a direct information about the hypotenuse. So tangent is probably the best choice. So what I write here, I would write tangent of theta is the opposite side, which is x over the 2. Yes? Because that one is also fixed. So this, in principle, if I want to simplify it, x becomes 2 tangent theta. But be careful. X relates itself to theta, but both of them are functions of time. X changes over time, theta changes over time as well. But how they are related at any instant of time, this is the relation. And because I am interested in knowing the derivative of x with respect to time, somehow I should differentiate this equation with respect to time. But if I differentiate the left-hand side with respect to time to keep the equality, I have to also differentiate the right-hand side with respect to time as well. So I would write it as dx dt. It is equal to d dt, 2 tangent theta. Okay, but this is simple. So dx dt, I keep it. Do you remember the formula for tangent, the derivative of tangent, because 2 is constant? So what should I write? The derivative of tangent? I don't know. Do you remember? 1 over cosine theta squared, which is called secant theta squared. Or of course, you can also write it 1 plus tangent theta squared, depending which one you prefer, okay? But, okay, it doesn't matter. Let me write this secant squared, yes? Secant is just 1 over cosine. Okay, let me not use secant if you are not very familiar with that, not to confuse you. So it becomes 1 over cosine theta to power 2. But do you think that, oh, there is a 2 here, sorry, there is a 2 there. Okay, but is it finished or not? Yes, because I am differentiating not with respect to theta. If I were differentiating with respect to theta, if this t were theta, then of course this is the end of the story. But I am differentiating with respect to time, so theta is a function of time, so I have to multiply it by... Yes? Is that understandable? Because when I differentiate tangent of u, I should write 1 over cosine squared u, pretending u is x, but it is not finished. I have to multiply by u prime. So that u prime takes that form, d theta over dt here. Understandable? Mm-hmm. Okay. So, this is wanted in this problem. Where was it? Yeah, this is wanted. And this is given because at any instant of time, this number is fixed. It is 6 pi radians per minute, so this is given. But in order to answer the question, or of course 2 is also given, I need to know theta. At which time? At the time that x is 4 kilometers. Okay, so I have to calculate the appropriate theta here. So this means that at that moment in time, so what is theta? I would say that tangent of theta is x over 2. Yes, but in this problem x is 4 over 2, so this becomes 2. Okay, in principle that is not wrong to write theta is arctangent of 2, because tangent of theta is 2, so theta is arctangent of 2, and then you can put it back here. But then of course you will not get the whole point, because this is possible to calculate its exact value. So don't do that. So the question is that, if I give you tangent of theta to be 2, can you find the exact value of this quantity? Yes, the formula is on the board. Yes? So 1 plus tangent theta squared is equal to 1 over cosine theta squared. So if I put 2 here, it becomes 5 is equal to 1 over cosine theta squared. So even without knowing cosine theta, I know this quantity is what? Is 5. So then this means that my question mark dx dt, this is equal to 2 times 5 times 6 pi. So this becomes 60 pi radians per minute. Sorry. X is a length. Length is being measured in kilometers, so it becomes kilometers per. Time is being measured in minutes.
Where did the rat go?
Hmm?
Where did the radians go?
Where the radians go?
Yeah.
No, the radians are cancelled actually.
How?
So you see, radian does not have any units. Radian is unitless.
Okay.
Yes. So dx dt. So what I am saying is that x is a length, so it will be measured in kilometers, because if that's the reason I changed from revolutions to radians. Okay, so in principle, if I ask you what is the dimension of omega, it's 1 over minute. Radian is dimensionless. Yes? Understandable or not? So my calculation is correct, isn't it?
It is.
Yeah, it is. Yes, everything is correct. So if I ask you what is the dimension of this omega, the dimension of this omega is 1 over time only, because radian is without dimensions. So if you have you seen this formula? So if you have theta measured in radian, and if this length is L and this radius is R, so L is equal to R theta. So if you express theta in terms of radian, it is the division of two lengths. So it's dimensionless. Yes. Okay. Is that understandable here? Okay, one more problem, and then probably we can have a break, and then the next lesson is very actually simple. So another problem from the book. So let us read it together. A leaky water tank is in the shape of an inverted right circular cone with depth 5 meters and top radius 2 meters. When the water in the tank is 4 meters deep, it is leaking at a rate of 1 over 12 cubic meters per minute. How fast is the water level in the tank dropping at that time? Yes. Okay. So what the problem is that we have a tank for water. It is in the form of an upside down circular cone, right cone. Because they say circular because this cross section might be an ellipse as well. When I say circular, it means that this intersection is actually a circle. And when we say it is a right cone, because cone might be also tilted a little bit, so you might have this scenario of a cone. When they say it is a right cone, it means that this point and the center are aligned on the same line, on a vertical line. Okay, so a leaky water tank is the shape of an inverted right circular cone with depth 5 centimeters. So if I call this from here to here, capital H, the depth is 5 meters. And then the radius, let me call the radius capital R. The radius is also given to be 2 meters. When the water in the tank is 4 meters deep, so it means that the water is, so this is not completely filled, so here, so let us assume that this blue part is the water here. And this radius, at that moment that the radius of this part of the water is, okay, so let me call this small r, and let me call the depth of water little h. So little h, so we don't know about that, but little h is given to be 4 meters. at that instant of time, and then of course water is leaking out. Okay, and we know how fast the water is leaking out. So if I consider V the volume of the water, inside, according to the problem, the leaking rate is 1 over 12 cubic meters per minute. So in principle, the rate at which this volume of water is changing is this much. But because I am assuming V is the volume of the water inside, dV dt will be a negative because it is leaking out. Yes? How fast the water level in the tank is dropping at that time. So what is wanted? I want to know how fast H is changing. Okay? So do you think at the end we will get a negative number or a positive number? Negative, because I am assuming that V is the volume of the water inside. So the rate at which the volume is changing is definitely negative because it is decreasing, and consequently the height is also decreasing. So the prediction is that of course the number should be negative. Okay, so if you don't mind, let me clean here and then we go to the next part. Okay, so how should we solve the problem?
We can begin by defining volume as a function of R.
Because we have two quantities involved. Because you see, derivative of the volume is in the problem, something is given and something is wanted is the derivative of H with respect to time as well. So what do you think we will do? We need to find a formula or a relation that connects these quantities. What is the best formula here? The formula of the volume of the cone. So do you remember it? So volume of the cone is what?
1 by 3 pi.
1 over 3 pi r squared h. So I am writing it for the smaller cone because V, according to that, is the volume of the water inside. That's the correct formula. Little r and little h. Okay, so, but what should I do now, for example? I can immediately start differentiation, but then you will see that I will have some problems. If I start differentiation, this is the product rule. So if I start differentiation immediately, okay, can you help me to do that? 1 over 3 pi is a constant, and that's a product rule. So I can copy and paste pi over 3 here, and then when I differentiate this one, what should I write? It becomes 2r, but dr dt plus times h. The derivative of the first one is this part multiplied by the second one plus the first one multiplied by the derivative of the second. Is that right? Mm-hmm. So when I differentiate, I get this. So what are the quantities I know? What I want, so this is given to me, minus 1 over 12. This is wanted. Okay. Do I know something more? I know little h. So this is also given. But in order to calculate everything, because I have only one equation, so I can have at most one unknown, and that is my unknown. Everything else should be known to me. Okay? So what are the unknowns left for me? This quantity is something I need to know, and this r is something I need to know. If I know them, I put them in place, then I have the question. So how can I find them? So I need another route, yes.
So you can notice that if we take the edge of the cone, and then you have h and you have r, the ratio between little h and little r is the same as the ratio between big H and big R.
Yeah, exactly, because this bigger triangle, hopefully you know, this is similar to this smaller triangle. So the ratios are the same. Understandable for everyone? So in principle, what I can write the ratio of, it doesn't matter which one you write, R over H is definitely equal to R over H. Yes? So, but R and H are constants and are given because these are the dimensions of my tank. They are not changing. So I know R is 2 and H is 5. So it is 2 over 5 is equal to R over H. Either You could do it in this way. I don't know which one is preferable for you. You could write everything in terms of one of these variables and then do differentiation. Might be that is simpler. Or you can also do it here. So if you don't mind, you can continue this way yourself, but might be this is the optimal way to do it in this way. I would write it as 1 over 3 pi r squared h. I have a relation between r and h. So what do you think we should do? I need to eliminate one of them in favor of the other one. Okay? But because the quantity I am interested in is dh dt, so let us get rid of r. So if I want to get rid of r, what is r here? R is 2 over 5h. Do you agree? So if I want to get rid of r, so this is working, but this is preferable now. So I would write pi instead of r, I put 2 over 5h, and then to the power of 2, and then I have another h. Then you see it is a little bit simpler. So it becomes 4 over 25 times 375, and then I have a pi, but I have h squared here, another h, it is h cubed. So that's a good relation because it really connects v directly to h. And now I differentiate with respect to time. So that was not wrong. You can just do it again and put the values here. But this is more, I think, efficient. So I would write dv dt. So this is just a constant multiplied by the derivative of this with respect to time. So we pretend as if h is the variable, so up to here. But I have to remember to multiply dh by dt. Is that right now? Okay, but now instead of dv dt, I put that minus 1 over 12. And this 3 and that 1 is cancelled, so it is 4 pi over 25. And what is little h? H is 4, so it becomes multiplied by 16. And dh dt is exactly the number that I am looking for. And I hope that you can do the calculations to yourself. dh dt that I am looking for is this number, whatever it is, divided by that one. And as we predicted, it becomes also negative. Is that clear? Okay, so there are not that many of these kinds of problems in the exam or in the workshop problems, but they have mentioned in the reading part that you need to be very good in these calculations. Okay. Any questions? Yes?
How did we eliminate h from that last part?
No. This h is given. 4.
Oh, really?
Yes. I put 16 here. So 3 cancels that one. H to the power 2 is 16. Is that right? Okay, so we can have a break for 5 minutes now here.